Let's start. Today we continue consider the conic section, and the main claim of first part of our lecture, classification of conic section. On the previous lecture, we consider the conic section in the partial case, namely, we consider the case when the conic section is defined by the following equation. I recall that in general case, a conic section is a curve which is defined by the following equation. By the following equation. More precisely, we have the set of the point which satisfy the following equation, and this equation is called the equation of conic section of the curve of second order. And conic section is an arbitrary second order curve. And on the previous lecture, we consider the partial case when the coefficient b is equal 0. And in this case, we obtain the first step of such classification. I recall that after enough simple transformation, we consider the following transformation of the equation of the curve. We simplify this to group of variable, and we can rewrite in the following form. First of all, we suppose that the coefficient A and C, maybe one of them, is not equal 0. And we consider two cases. First of all, both of these coefficients is not equal 0. And second case, when A is not equal 0, but C is equal 0. And in the first case, we obtain the following equation after simple transformation. Let's denote the last term in this sum by f prime. And we reduce this equation to the following form. And we obtain in the case when we consider two cases when the coefficients minus f prime, the ratio of minus f prime to a and minus f prime to c have the same sign, and this sign is positive. In this case, we obtain the ellipse. The second case, when these coefficients have the both sign, but the negative sign, this sign is negative, we obtain the case of image ellipse. In the real plane, this curve has empty set of points. Empty set. But in the complex plane, this curve, which is called image ellipse. In the case when the coefficient minus f prime, the ratio minus f prime to a and ratio minus f prime to c have the various sign. In this case, the product AC less 0. In this case, we obtain hyperbola. In both cases, we obtain the so-called central curve. Central curves. In these cases, we have the so-called center, which is center of symmetry of this curve. And in the case 2, when the coefficient c is equal to 0, after the same transformation, we obtain the following equation.
Can you please move the camera? Can't see the board.
And we obtain the following equation.
I'm sorry, Professor. Is there anyone?
Yes. Mhm.
Minus f prime over a greater than 0 minus f prime over c greater than 0. Because you have minus f prime over a twice.
Yeah, and in this case we have the negative number.
Where's c?
C?
Anywhere here.
Oh, this case.
First and second.
First and second.
You only have minus f prime over a greater than 0 twice.
Great.
Or minus f prime over a greater than 0 minus f prime over c greater than 0.
Ah, okay. Thank you. Thank you. Yes.
For the second.
Yes. See, yes. The same.
Second case.
Ah, yes. Thank you. Mhm. Thank you. Yes, and in this case, this number be the coordinates of the center of this curve. And in this case, we obtain the equation in this first case when these numbers have the same sign and the sign is positive, we obtain the ellipse and the x0 and y0 are the coordinates of the center of this ellipse. And in this case, we obtain a curve which called parabola. But in this case, we suggest that E is not equal 0. When the A is equal 0, we obtain in this case the equation in this form. And if f prime greater or equal 0, we obtain pair of parallel straight line. In the case when this number less 0, we obtain the empty set, and when this number is equal 0, we obtain two coincide straight line. And we obtain all cases for the curve of second order. But we suggest that the coefficient b is equal 0. Now we consider the general case, and using rotation transformation, we reduce this general case to this partial case. Using rotation, matrix of rotation, we kill this coefficient and reduce the general case to the partial case when this coefficient is equal 0. And let's start. Now we suggest that we have the general case. And this coefficient is not equal 0. on the first lecture, we consider the transformation of rotation. And I recall that this, we have two coordinate or reference system. First of this coordinate system, x 0, y. This coordinate system has the origin O and basis, orthonormal basis E1, E2. And so-called old coordinate system. And we have also x prime, O, y prime, a new coordinate system. And let P is arbitrary point which has in the old coordinate system coordinate x, y, and in the new coordinate system, this point has the coordinate x prime, y prime. And we have the following relation between old coordinates and the new coordinates. X, y, expressed in terms of x prime, y prime by the following formulas. X prime cosine phi minus y prime sine phi, y is equal x prime sine phi, y plus y prime cosine phi. And using the matrix notation, we can rewrite these equalities in the following form. We can use the matrix of rotation, cosine phi minus sine phi, sine phi, cosine phi, x prime, y prime. And we used the following notation. This matrix is transition matrix from old base E to the new base U. And this matrix we denote by P, E, U. If I'm sorry. And if we use the notation x, e, the coordinates, the point in the base E, and we use the notation xu for coordinates of the points P in the new base U, and we obtain the following formula: xe is equal PEU xu. We have two following basic formulas for relation between old and new bases and between the coordinates of point in the old bases and in the new bases. These formulas are dual one to other. this the same matrix, and in this notation we multiply from right side basis E. Basis E is a matrix row E1, E2, and U also matrix row U1, U2. XE is a matrix column XY, X prime, Y prime. Okay, now we using this formula and this substitute this expression in the equation of our curve, we choose the angle phi. So after the substituting and some transformation, we obtain that the new coefficients b prime, the coefficient this product x prime and y prime is equal 0. This is our claim. We must to choose this angle such that this new coefficient is equal 0. And we need only consideration of the main term, the term of maximal order, maximal degree. This term which has the degree 2. x2, x, y, the sum of the degrees is also 2, and this term is term of degree 2 also. We can calculate and obtain the new formula by two ways. First of way is enough naive way, substitute this expression in this formula. And second way, using the matrix notation. First way. We substitute this expression and in the x and y using this formula. We can change in this expression y by this formula, and we have x prime cosine phi minus y prime sine phi y. I substitute this expression, this x in this formula and this y in these places when we have x and y correspondingly. I need only the expression which contains only second degree terms, and claim to kill the coefficient which coefficients with terms products x prime and y prime. And I now need to consider the term of the first order. And after simple transformation, we obtain the following formulas: x prime square cosine square prime plus y prime square sine square phi minus 2x prime y prime cosine phi sine phi plus 2b x prime square sine phi sine phi minus y prime square cosine phi sine phi plus x prime y prime cosine square phi minus sine square phi. This expression half sine 2 phi. This expression half sine 2 phi, and this expression cosine 2 phi. This expression sine 2 phi half plus c c is the square of this expression, and we obtain x prime square sine square phi plus, oh, I'm sorry, y prime plus y prime. Yes, okay. X prime square plus y prime sine cosine square phi plus 2x prime plus other terms of the first order. And I need the following term: x prime square, x prime, y prime square. X prime square. This term, this term, and this term. C? Ah, C, yes, C. Y prime, okay, thank you. This prime square and y prime, yes, y prime. X prime square. A cosine square phi to B 2.5 kill by one other sine phi and plus C sine square phi plus, oh, I'm sorry, and term before the coefficient before product x prime, y prime. This term, and this term. We obtain minus a sine 2 phi plus cosine 2 phi plus C sine 2 phi and plus this term, and the coefficient before y square or y prime square. This term, this term, and this term. Oh, no. This term. First, a sine square phi. This term. Minus b sine 2 phi plus c sine phi, c sine 2 phi. I'm sorry. Cosine square. Cosine square phi. Yeah. Oh, cosine. And plus the sum terms. Let's denote this term by 2d prime x prime plus 2e prime y prime plus f prime is equal 0. We obtain the sum term on the first order. And we need that this coefficient will be equal 0. These coefficients we can write in this form: c minus a sine phi plus 2b cosine phi. Cosine phi is equal 0. And in this case, we obtain that answer to phi sine to phi to the ratio to be a minus. I change the sign. We can rewrite this equation in this following form, and we obtain that the ratio to be a minus c is equal tangent. I'm sorry, to phi, tangent to phi. We obtain the sum condition if we choose the angle phi such that the tangent of this twice angle to phi is equal this ratio to be to the difference between a and c. We obtain that in the new reference system, this coefficient before x prime y prime is equal 0. And we reduce this case to the previous case. One more remark. Yes. Easy to see that we can denote but this coefficient by a prime and this coefficient c prime. Let's summarize. A prime plus c prime. We obtain that term and that term because cosine square plus sine square is equal 1. This terms has opposite sign, and its sum is equal 0. This sum cosine square plus sine square is equal 1, and we obtain that I prime plus C prime is equal A plus C. Is equal. In our situation, this coefficient is equal 0, and we have that C minus A sine 2 phi plus 2b cosine phi is equal 0. And let's calculate the other sum. Let's calculate my claim to prove the following formula. The product A C is equal A prime C prime is equal A C minus B squared minus B squared. Let's calculate this expression left side. A prime cosine square phi plus B plus plus C sine square phi plus B sine 2 phi multiply A sine square phi minus plus C cosine square phi minus B sine 2 phi. And okay. It's, in my opinion, most hard way. First of all, let's note that from this equation we can deduce that a squared plus c squared is equal a plus c, and a minus c square is equal a square plus c square minus 2ac a minus, and easy to see that the difference a square minus c square is equal a cosine 2 phi plus 2b sine 2 phi, and minus c cosine phi, and we obtain a minus c cosine 2 phi, a minus c cosine 2 phi plus 2b sine 2 phi, and easy to see that difference is equal 0. And if we subtract from first equality, second equality, we obtain that a prime plus c prime square minus a prime minus c prime square, which is equal 0. This difference is equal I'm sorry, 4 is equal 4 AC. 4 AC. This difference is equal 4 AC, and we obtain that the square of this sum I'm sorry. We obtain that the following equation, this difference A prime plus C prime square is equal for a C. And this difference is equal AC minus B square. Sorry. Sorry, miss. Maybe mistake. We obtain that this term is equal 0, and A minus C minus A sine 2 phi plus 2b cosine phi is equal 0. And we have also A prime plus C prime is equal A plus C. Okay. We have two equality. A prime C prime is equal A plus C. And let's calculate A prime minus C prime. A prime minus C prime. Let's consider this difference. And we obtain A cosine. Cosine 2 phi, yes.
No, I'm saying you
Cosine.
already B prime minus C prime.
C minus. A. Нет, yes. C minus A sine 2 phi. Yes, that's right. That's right. And
Right. What you said.
can you show? Where is mistake?
You already have B prime
Ah.
minus C prime.
Yes. Yes. We have, yes. Thank you. We have this, this one. Cosine to phi, yes. Plus this a minus c cosine to phi plus 2b sine to phi. Yes. Okay, and we have this term is equal, and after them we can calculate a prime minus c prime. A prime minus c prime. We can a minus c prime plus okay, let's calculate this square and to add this square, and direct calculation. We obtain a minus c prime cosine square to phi plus I consider square of this expression and square of this expression. Add. Maybe more simple calculation.
И закрутить еще.
And easy to see. Easy to see. We have in this case we have sum and difference, the same expression. We have the sum, and in this case we have the difference. And we can see that this cosine to phi and this sine, this opposite way, cosine and sine. And we have a plus b square, a prime minus b prime square, and we obtain a prime to a and b plus b prime plus a prime minus 2a prime b prime plus b prime. And easy to see that this expression ab and a prime b is equal. And we can subtract from this we have the product, this term and this term, this term and this term, and this product have the opposite sign, and we can subtract from this expression and this, and we have also the sum of this square and this square, this square and this square. These have the same coefficient and product, in this case cosine square, and in this case sine square. And we obtain that this equal a minus c square plus 4b square. 4b square. And we obtain a square minus c square is equal, I'm sorry, to Yes. We obtain this this equality. And we can also a square plus c square is equal a plus c. And we can to add this expression and this expression, and we obtain a square plus c square and after I'm sorry, minus 2ac, minus 2ac. We can, okay, we can subtract from this equation. From this equality, we can subtract this equality, a square, c square, and we obtain 4 a square c square is equal 4ac minus 4b square, and we obtain a prime c prime is equal ac minus b square. We finish this calculation. Is a naive way to obtain this equality. So we obtain two equality. First of all, a prime plus c prime is equal a plus c, and second, a prime c prime is equal ac minus b square. Later, we obtain indirect way to prove this equality. Some words about this other way. We can consider our equation using the matrix notation. Let's consider the terms of the second degree. We have 3 terms of the second degree, and our claim to simplify this this part of equation of our curve using the rotation. We can rewrite this equality using matrix notation. Let's introduce the following matrix: A, B, B, C. And we can rewrite this equality using this matrix notation. Easy to see. You can rewrite this equality as ax plus by, bx plus cy. And if we multiply this matrix row on this matrix column, we can multiply this term on this term, and after them to add this expression, we obtain ax squared by plus bxy plus byx plus c y squared. We obtain final expression. And our claim, we write this expression in this following form: xy, x prime, y prime, a prime, 0, c prime, x prime, y prime. You write this expression in this form. We have the following matrix transition, which expressed coordinate in the coordinates of the point in the old system in terms of the coordinates of the point in a new system, and we have we can using transposition operation, this equality we can write in this following form. Using transposition, I recall that if we have two matrices and we apply transposition to the product of the two matrices, we obtain the product of this matrix in the opposite order. And from this observation, we obtain that matrix rho x y is equal x prime y prime, and transpose this matrix cosine phi minus sine phi cosine phi. And this equality we can write in this following form: x prime y prime cosine phi And our claim to choose the angle phi such that this product of the matrix is equal A prime C prime. And we obtain the following final equality. Easy to see that this equality is equal equality of the trace. I'm sorry. The quality of the trace of this matrix and this matrix. And the second equality is equality of determinant, this matrix and this matrix. We have two matrices, A, B, B, C, and this matrix A prime, C prime, and this two inverse matrix. And we have the following property of the trace. The trace product matrix AB is equal trace of product matrix in the inverse order. And from this property, we obtain that trace this matrix and this matrix is equal. If I apply the trace to the left side and the right side, I obtain I can change the order of this product, and after changing, I obtain this. And these two matrices, this matrix is inverse to this, and this product is equal a unit matrix. And we obtain that this trace is equal this trace. And we obtain this equality, this first equality. And we have the second property of determinant. The determinant of the product of two matrices is equal product of determinant of this matrix. And using this property, easier to see that determinant of the left side is equal the product AC minus B squared. And the determinant of the right side is equal product of A and C. And using this property, we can conclude these two equality from general properties of determinants and matrix. So we can understand what the kind of the curve using the equation of the initial curve. For example, if we have that AC minus B squared is not zero, we obtain that in this case that our curve is central curve. Other words, this curve is a type of the ellipse or hyperbola. I mean that this curve is not exactly hyperbola or ellipse. This curve can be image ellipse, maybe pair of parallel curve, and so on. But the type is type of central curve in this case. Also, we can use this determinant, and we can, for example, if this product is not equal, but this expression is equal zero, we obtain that in this case we have exactly ellipse type. Also, we can use this expression as this expression. Easier to calculate the difference between this expression. And I have no time, but I can formulate the last theorem. How to calculate the coordinate of the center of the curve of the second order. The theorem, the coordinate x0, y0 of the center of the central curve satisfy the following equation: ax0 plus by0 plus d is equal 0, bx0 plus c y0 plus e is equal 0. This system of linear equation is uniquely defines the center of the curve of the second order. of the central curve. I have no time, but in the next lecture we continue and we will prove this theorem. This proof is a direct calculation. Thank you for attention. I'm sorry. The question. The question: why we need that this curve will be zero? My explanation is following. We consider, first of all, we consider the case when this coefficient b is equal to 0. And in this case, we obtain the classification of such curve. We solved this problem in this case. And the second step, to reduce the general problem to this partial case. And for this, we need to obtain the case when this coefficient is equal to 0. And we obtain using the matrix rotation. Rotate the coordinate system. We choose the angle of rotation such that in the new coordinate system, the coefficient b is equal to 0. And after them, we can obtain the classification of the curve. Thus, we simplify